Alrighty, so before the lecture, let's talk about your upcoming programming test number 1. Right, I'm still finalizing the guide PDF for giving you all the information you will need, but these are the details I can confirm right now. So you can definitely get started. It's going to happen on the Monday right after the reading week. If you look at the semester calendar, it's on February 27th. And similar to your written test number 1, you will not come to here, the lecture hall, you will go to the William Small Center, the same room. And it will be during the class time on that particular Monday, and you'll be given 1 hour to actually do the programming test. I will make sure you're given about between 2 and 3 programming tasks to actually solve. I also try to give you guys some example questions. You can expect the PDF guide to be released by the end of tomorrow. And also early next week, I will also release some example tests for you. And after your submission deadline for assignment number 2, you will also get a solution right away. So you can also study for about a week. So hopefully that will be enough for you to get prepared. And I want to emphasize again about how important it is for this part of the study. Okay. So let me just go back to E-class very quickly, and then I'll show you where it is. Okay, hopefully I can just log in. Okay, if you go back to your E-class, and then you will see that, oh, by the way, so these are the 3 TAs you should really contact if you got any trouble outside the office hour. So they are over there available for you if you want to debug your code. All right, if you go to the E-class site and try to look at, over here, assignment number 2. If you look at assignment number 2 instruction over here, all right, it is very important for you to note over here. Right, you can see under page number 4. This is optional, but if you got any trouble programming some operation for linked list, I'm pretty sure one of these will give you some nice inspiration for you to get started. So in addition to what we cover in the lecture, you can also see some additional problem solving to really walk you through the reasoning process. If you really find a need, you definitely should check them out. That's one thing. And what's really required would be for you to know how to really do generic linked list. So we are not going to spend time in the lecture. So I think the best way for you to learn would be watch some video and practice right away for assignment number 2. Right? And here are some reminders for you as well about the syntax. This will be what you'll be expected to do in the programming test number 1. All right? So study that. If you need help, let me know. Okay, let me just go back to announcement quickly. So for your programming test number 1, it's going to cover assignment number 1 on recursion, and also assignment number 2 on the generic singly linked list. The lecture example we did so far was just about singly linked list of strings, just a string value. But you ought to know how to do the generic version, which is covered in assignment number 2, right? Just make sure you study that. And for assignment number 1 solution, I already gave you all the references. If you want to discuss any walkthrough about this assignment 1 solution, reach out. All right. Yes? Sorry, say again? I'm afraid not. It's a good try. All right. All right, guys, any question? We okay? All right. If you are okay, let's now move on to finishing off the singly linked list, and then we also need to talk about doubly linked lists today as a continuation for the study. I will hopefully go over a good part of it, but we may have to continue after the reading week. We'll see how that goes. All right. Okay, so let's now continue with this. So what we talked about last time, we talked about the various operations on the singly linked list. We talked about Java code, we talked about tracing, and also we talked about how you can analyze the running time by looking at the code. Okay? And what we would like to continue today is to finish off a few more operations on the singly linked list. I think these are definitely all the basic ones you will need to know. Okay? Let's now take a look. And this one is something we sketch very briefly about how you can remove from the end of the list. Let's say this is the list you have, right? You can see the singly linked list object pointing to a chain of nodes over here. And let's say our goal is to remove this particular node. However, if we only got a reference of a tail, right? That's the attributes that we introduced as we talked about last time. If you only got a tail reference, it would not be enough for you to really remove this node, because the critical step for you to remove this node would be, so guys, please, all right? You might think your volume is pretty low, but it's quite obvious to me, please. I'll really appreciate it, okay? Thank you. All right, if you try to remove this node over here, and then the critical step you really need is to find out the second last node over here, and then set its reference to be null. That's really the critical step. But this one here, we don't really keep any reference to it. So the problem is, how do we find it? We need to call a helper method, which is the get node at, right? This will be the second last node. That's what we need to do, right? So that's the critical part you want to really watch out for the remove last. And we'll analyze the running time in a bit, but let's do some very simple tracing. And the JUnit test code over here is something I made available to you. Please go over it and also play with it, okay? Let's now take a look. This part over here is something we already talked about, how you can build the chain. Let's say we got Tom, Mark, and Alan. Since we say at first, so we got Tom, Mark, and Alan. And what we want to do is try remove last over here. Let me try one of them, and then maybe the other two you can try to trace by yourself. They are quite straightforward. You just need to know how we can set up the references accordingly. That's the important part, okay? Let's now just look at this one here, okay? Remove last. And let's try with this. The way to do it would be, we're going to call this remove last over here. And currently we got size 1, 2, and 3. So this part here is not going to be executed. It's not a boundary case. We're not trying to remove the last when the list is empty, so there's no error. Is the size equal to 1? Also no. It's not also the special case. If there's only one node in the list, in that case, removing the last would be the same as removing the first. It wouldn't make a difference, all right? So let's now talk about the else part over here. This is really critical, right? Only a few lines, but you ought to know how exactly we're setting up the references by these lines of code. You will see right away, we are trying to call a helper method over here, okay, this line here. So what are we saying? We're saying that there should be a local variable called second last node. The name itself is quite obvious about what it should do. And then get node at size minus 2. Think about what size minus 2 is really doing, okay? Think about it. Okay, so here you can think about size minus 2 is a valid index for sure. We know pretty well size minus 1 will be the index of the last node. And if we minus another one, which is minus 2, in that case, it's going to give us the second last node. That's why we have the name over here. All right? So by calling this helper method here, which I'm not going to trace in detail, we did that last time. This one here is going to return, think about the size would be 3. And then minus 2 is going to give you 1. That means we're going to return index 0, index 1. This will be the node that we want to return, which is the second last node. All right? So what's going to happen is we're going to have a reference pointing to here that would be the second last node. All right? Any question with the first line? All right, the second last node. And then the next one will be this. Right? What about this one here? We say that we want to set the next reference of the second last node to be null. What are we trying to do? Let's just follow faithfully and see what's happening here. So what we're doing is, for the pink one over here, we're saying that the second last node is pointing to this. And we're going to set its next, rather than pointing to here, it's going to be null. Apparently, we are trying to detach the current last node from the chain. That's what we are trying to do. Sorry, today I'm just a little bit sensitive to all the noise. All right, so here, we are trying to do the second one here. We're setting that to be null. And after this, we are going to update the attribute as well. Because this one used to be the tail, you can think about. This one used to be the tail of the singly linked list. And what we do is, rather than pointing to here for the tail, it's now going to point to this last node. That's exactly what this one is doing. And then after that, we should also decrement the size. Used to be 3, and now it should be 2. Right? That's about the remove last. It is so important for you to know the following. For the remove last, it's not enough just to use the tail of the list to complete a task. You ought to know where the second last node is. To know that, you have to really get node at size -2. That's really the critical part. But later today, we're going to see how we can resolve this issue by, again, trading the time by space, by introducing another attributes at the node level. Is why we need a doubly linked list. So remove last is really where we can transition from singly linked list to doubly linked list. That's where the critical part is. Okay. And what about the running time before we pause for further question? Apparently, this case over here, if we ever got error, or if we ever got a boundary case, no loop, it's just constant time. And what about over here? Again, like the last time, there is no explicit loop. But since you are calling this over here, so that means you still, in theory, in general, you still have traveled all the way to the second last position in the list. So that one will be linear time, right? That's why this method call here will still dominates the running time. So this is where the running time is going to be dominated, right? Yeah, if you look at the slide, it will explain to you, overall, it's going to be big O of n. Okay. Any question about this? So I would say remove last doesn't really take that many lines of code to really implement, but it's really conceptually important. Especially later on, whenever you compare singly linked lists and doubly linked lists, always remember remove last is where the distinction can be. Mario. Good question. Yes, let me explain. Yeah, I know what you want to ask. Very good. Mario question goes like this. Let's say before the removal, this used to be the last node. After removal, we only try to set the next of the second last node to be null. So what does that mean? That means this node over here, if there's no other node that's pointing to it, what's going to happen is there will be some automatic garbage collection mechanism that's going to happen in Java. So at some point, you can assume that at some point, the garbage collection is going to get rid of this object by freeing the space. That's something we don't have to worry. It's automatic. Okay, I'll make a note here. So this will be garbage collected. And for your information, the garbage collection process is quite a sophisticated one. That's why it's automatic. It can take another course to actually explain the theories behind or how to implement it, but we don't need to worry. All you got to know is if there's any objects that has become isolated with no further references pointing to it, in that case, it will be garbage collected at some point. Okay. All right, any more question about remove last? We're good? Yes, question. Go ahead.
Not to get into garbage collection, but essentially what we're saying, because we're removing the reference to that node from a previous from the previous chain in the link.
Yes, the first question again is just emphasizing what I just mentioned. By setting the second by setting the second last node. Yeah, sorry. By setting the second last node, let me just reconnect my pencil. Sorry. Yeah, by resetting the second last node's next reference to be null, what's going to happen is this node just becomes what they call an orphan node that has no other references pointing to it. So that's why we can assume it will be garbage collected, but you don't need to worry.
Even though there's one element,
yeah, exactly. Yeah. Of course, there might be some sophisticated story behind, but we don't need to worry for now. You can assume that if that node has no usefulness considered by Java, it will be garbage collected. But as far as the chain of node is concerned, so now what will be the tail? Only this one here. So this node here is not relevant to us anymore, so we don't have to worry.
okay. I asked because there's still a
Yeah, that's okay. Second question.
Second question. We're saying this is all n because of the get node at
Yes.
method. Is that because we said earlier the get node at was off in itself, or is
No, the get node at over here is really meant to give you the second last node. So if you look at here, this one here is always going to be size minus 2. And this one is quite obvious because size minus 2, think about size is like an n. N minus 2 asymptotically will still be n. That means in general you still have to go over the next references traversal for n times in the loop. So that's why it's going to dominate the running time. Okay, very good. All right, any more questions before I move on? Okay, let's now move on. So that's about the remove the last, and then let's now try to do some very simple exercises. And as usual, well, as last time, I'm going to give you some conceptual sketch about how this method can be implemented by drawing some diagram, showing to you what the critical steps should be. And your job is to go back to the starter project I made available to you and implement these methods. All right, that's what you should do. So what we want to do is we want to see. Let's say I have a method over here. Let's say in the simply linked list class. And the method is a mutator, doesn't return anything. It's going to take some node as an input. So if you look at your assignment number 1, it's kind of assignment number 2, it's kind of similar. You're given just a node somewhere in the chain, somewhere, not necessarily the beginning. And then what we want to do is we want to insert a new node storing this string value after n. All right, that's what we want to do. And let's take a look at how this can be done. It's incredibly simple. Okay. Number 1, you want to know the following. I will highlight it. If you look at this one here, it is an input that's given. So this is given as input. That means there's no need to call get node at. Sorry? It was similar, but I think what we did last time was like at first or at last, something similar. But this one will be a little bit different. They're kind of similar, so that's why I don't have to show you the Java code. Yeah, similar. Okay, but I can go over this quickly. All right, for this one, what should we do? What's going to happen is we're going to create a new node. Okay, I'm going to create a new node over here. This will be step number 1. Okay, step number 1, create a new node. And that new node over there is going to, let me draw a little bit too. This one should be fine. Right, the new node has the objects, the element site, element field pointing to this. And what about its next? All right, go ahead. And the next, exactly. So think about in general. So this structure over here is telling you this might be just an arbitrarily long chain of nodes. The node that we want to insert after, before that, there might be some node. After that, there also might be some node. So that's why you got to handle the cases carefully. Okay, there might be a node right after n.next, right? So if you take a look, there might be a node over here. So this one here would be n.getNext. All right, so what should we do? What you should do is, if I want to insert this node right after this, I want to make sure that node also points to its next to n.getNext. That's how I insert in between. All right, so let's now outline the steps. So you will have to make sure number 2, you want to make sure this one here, the next, is pointing to here. The new node next should be equal to n.next. I'm just sketching the code over here. So this will be step number 2. And step number 3, you have to make sure this node over here, because I'm inserting this new node after that. So its next should no longer be this one here. It should be exactly the new node, right? So that'll be the final step. Okay, so this will be step number 3. So n.next somehow should be changed to the new node. All right, pretty straightforward, but you have to make sure you do the references setting in the right order. If you try to change the order around, it might not work. All right. And of course, you also have to make sure you change the size because you're adding one node, right, to the list. All right. Are we okay with this? It's a sketch, That should be sufficient for you to write the code. All right. What about this guy over here? Oh, sorry, before that, what would be the running time for this operation over here? Would it be constant? Be constant, right? Because here we are not using any get node at. That's really important insight. Okay, no need. All right, so this one will be constant time. So remember the kind of exercise we did earlier when I tried to intuitively sketch selection sort versus insertion sort. Even just after drawing some diagram or sketching around, we can already see the running time. Similar here, just by drawing some diagram about how we can change the list structure, you can also derive the running time accordingly. So again, it's a very important technique I wish you guys will pick up. Question somewhere? You okay, right? Oh, okay, sorry. I thought you were. Oh, you. Go ahead, please. All right, you're thinking too much ahead, but that's okay. All right, guys, I'll give you guys some time to think about. Let's think about, first of all, what's the problem? We got another method over here. And we still got some input parameter over here, and we have the reference to that node directly somewhere in the middle of the chain. What we want to do, instead of inserting some node after, we want to insert some node before. Let's say this is node before that. We want to make sure now you'll be the new node, and the new node will point to this node. That's what we want to do. Now, do you think it's going to fundamentally change the running time? It will be, right? It's pretty much like a remove last problem. Because in order to insert before, you have to make sure you can set the previous node's next reference to the new node, right? Let's now try to sketch the idea quickly. What I'm going to do is I'm going to, first of all, create a new node over here. Let's say 1. And then that node there is going to point to, for the element field, over here. This is the element. Okay? And then we have to make sure we also find out where the previous node is. You can think about this one here is the node before n. And this one here, you cannot exactly do like a get node at. Because get node at that we discussed earlier, you have to give an index. You don't necessarily know what index it is for this one here. But presumably, you can just write a while loop to say, I'm going to check the current node. As soon as the current.next is equal to this node here, I know I'm reaching that. Okay, I'll write down the hints for you. How do you find it? So you need a while loop. Current node dot next not equal to n. So as soon as it is equal to n, you know that you will exit from the loop and can return the current. Something like that. Right? That'll be hints for you. Right? Think about this guy here would be step number 2. And even for the step number 2, you already know it's going to be big O of n. Because to really get to that previous node, what if n is pretty close to the end of the list in general? In that case, getting the node before, it will be asymptotically linear. So I can write down linear for this step already, big O of n. Right? Once I find out this node, we're pretty much done. How do we set the references? Number 1, you want to make sure this new node.next is going to be n.next. New node.next should be assigned to n.next. Very similar to what we did over here. And then you want to make sure the previous node over here, rather than pointing to n, is now going to point to this one here. So the node before dot next should be set to the new node. It's not exactly valid Java code writing, but I'm showing you the idea. Right? So the orange one will be step number 2, and this will be step number 3. And what's the running time? Because step number 2 over here already show, oh, you know what? I mess up with the number. Let me do it again. Thank you. Absolutely. This will be number 3, and this will be number 4. And we know that this part over here is going to dominate the running time. Overall, it's going to be big O of n. All right, question? Are you talking about step number 4? Oh, over here. So new node next would just be equal to, yeah, you can either say n or you can say the this node.next. Either way is fine. You can see, I really meant to say, yes, I know what you mean. Yes. Either you can say n, I see, that's definitely a mistake I made, n here, or alternatively, you can say the node before dot next. Because you would have got that local variable anyway, so either way will be fine. Yes, thank you. All right, either way. All right. All right, guys, any question about these two methods? Several things you want to pick up from this sketch over here. Number one, understand how these two methods really work. Number two, based on some conceptual sketch you can definitely do on the paper, you can already derive the running time. That's especially important. Number three, try implementing this in Java. It will also help you for the programming test, I guarantee. All right? All right, question? Yep. That's correct. That's exactly right. Because for this method here, let's recall what's really the input. Input is really some node for which I want to insert a new node before that. To really get some previous node in the singly linked list is very expensive, linear time. So that's, again, it will be another motivation. Maybe we want to trade space for time. That's exactly what doubly-linked lists can do for us. Guys, a very quick look ahead. It would be very nice to say, given this node, if I can have some very good reference to point directly to its predecessor, then that'll be constant time. But it's not the case for singly linked list. It's simply not. All right? All right, so that's the exercises over here. All right, so this will be another method for you to implement. So it's called remove at. Right? So this method here, you can just go to the starter code and try this one. This one here, you might need to get node at some point. Maybe. Right? That's something you can implement. All right? All right, a final page to conclude the singly linked list, and then we'll take a short break. Right? What we need to do is to really compare the operations between arrays and singly linked list. So this will be a summary. All right? Okay, so let's now take a look. Right, you already got a table on the slides, but I think it's good to really discuss point by point. You ought to know what's really being summarized over here. It contains much information. Why don't we start with something over here, array. Okay, if we got array over here, let's start with the operation that's actually cheap for both the array and the singly linked list. If you want to get the size of the array, you just say array.length. Or you got the size attributes from the singly linked list, right? So that'll be constant time. Also, if you want to get to the first versus last elements in the list or the array, also constant time. In the case of the array, you'll say a at index 0 versus a at index a.length minus 1. And for the singly linked list, you assume that you actually got size and also head and also tail. So that will make it just constant time. Again, trading space for time. Or big O of 1. All right, that one should be quite straightforward. And let's get to something a little bit more distinguishing between the two data structures. If I want to get to an element at index I for array, constant, indexing. What about for a singly linked list? Get node at, linear. Agree? What about removing the last element? If I want to remove the last element from the singly linked list, I cannot just use a tail. I need to get to the second last node, which will be big O of n. That's something we just discussed today. And what about removing the last element in the array? So here, I'm making the following assumption. So here, we're talking about no resizing for the array. And in that case, you can simply say, okay, so this will be big O of 1 for array. Let me write it down. You can say a at index a.length minus 1, and then simply assign to null. That's what you can do to remove the last element. No resizing. Of course, if you want to do resizing, then it might be linear, but let's not worry. On the other hand, these operations will be linear, right, for singly linked list. Okay? Let's now try to compare this part over here. So if you look at this part here, all right, this is the part of the table we are looking at. Okay, over here. And then we have, let's say if I want to add, remove first elements or add last elements. Think about in the case of the array. If I got an array over here, if I want to add something to the first, I need to put it here and shift everything to the right, right, by using a loop. Similarly, for adding the last element here, if I want to really create something here by resizing. So potentially, it's going to be linear time. Similarly, so here it doesn't really matter if you're given the reference or not. It's not relevant for the array. So for this part here, for array, it will just be linear. Let's start with that. Okay. For the singly linked list, let's start with this. If I want to add first, remove first, and also add last. So these three operations for the linked list will all be constant time, right? And then I want you to pay attention to this cell over here. Take a look at this one here versus this one over here. Okay, that's actually very important. If you take a look at this one here, if, let's say for the singly linked list, if I want to add, let's say I want to remove the ith elements. Let's say I want to remove ith node. But let's say I'm given the reference to I minus 1. So that would be as if somebody did the get node at I minus 1 for me. So in that case, I don't have to spend any efforts on that. So that's why that one there should be constant time. So that's why when you reveal this, you will see this. Think about this case over here is going to be still constant because I'm given the reference to the I minus 1. On the other hand, if I'm not given the reference, it's going to be constant. Sorry, linear. Beg your pardon. Say it again. If you want to somehow remove the ith element, let's say, if you're already given the I minus 1 as input, in that case, you don't have to call get node at I minus 1 anymore. So that will be constant. On the other hand, if you don't really have that reference given to you as input to the method, you have to call that get node at I minus 1. That will make it linear. All right? You really have to distinguish between these cases. In the actual question you might be asked, you have to be very clear about the context for each operation, what input you might be given. All right? All right, any question about this table here? Any point that's not clear to you? Ultimately, we are going to add another column, ultimately. And that one there is going to be doubly linked list and compare all the operation. That'll make it complete. Not too sure if we get there today, but that's really something we'll do very soon. Question? Sorry, which one are you talking about? This one here? Oh, I mean for this one here. Yes. Yeah, so this one, for example, this one doesn't really matter resizing or not. Let's say here, if we got this particular array, let's say you still got much space afterwards, that's null. If I want to insert into this particular slot, I have no other way, but I have to make sure, okay, I put a new element here, but I got to shift everything else to the right. That one is going to take linear time, no matter what. So resizing is not quite relevant for these, for array. It will just be linear anyway, because you got to do the shift. Yeah. Oh yeah, sure. Absolutely. I'm just saying, yeah, so the only assumption I'm making is for here, when I say remove the last elements, I don't really want any resizing. I just want to reassign the last element to be null. That one is constant. But if the context of the question tells you every time we do any operation, we're going to resize accordingly, then this will suddenly become linear, of course. So context is really important. Yes. All right, if no further question, why don't we take a short break? And then after the break, we can actually get on to doubly linked list. Why don't we take attendance of you? All right, let's now take a look. All right, let me start the poll, and then. Okay, yeah, you can check in, please. Yeah, you got any issue, as usual, come forward. I got a sign-up sheet for you. Everybody's okay? We're not doing attendance, just in case you don't know. Yeah, if you got trouble, come forward. Otherwise, I can wait for another 10 seconds. Very good. All right, done. Okay, we'll resume in 2 minutes, and we'll talk about doubly-linked list.
Registered my attendance, it didn't register my answer though.
Did you actually click on the poll?
Okay, I thought I did, but it just like didn't.
Drop by my office hour at some point. We can check on the actual spreadsheet if that's being registered. I cannot check it now, but maybe drop by later. We can check.
All right, thanks.
All right, good. Aisha, did it work? There we go. Thank you. Okay, we'll take 1 more minute, and then we'll resume. All right, we'll resume in just 1 moment. Alrighty, let's get started again. All right, so for doubly-linked list, just one more thing I would like to show you that you will see on the slides. So that's the table we just went over. And then in the next few slides, you will see the generic classes. So this is exactly what's really in the required background study for your assignment number 2, right? You gotta watch out for the videos, link from assignment number 2 instruction, and go through exactly how to interpret these 2 classes. So you want to also know about the node and also simply linked list. Now they are being generic rather than storing just string elements, okay? And so this is really something you should know, okay? And for your programming test number 1, most likely the list or mainly the node that you have the program will be generic, okay? And this will be something you have to watch the video to study up to here. Only 3 slides. Takes about less than 1 hour to complete a background study. Guys, it's worth your time. Make sure you do that, okay, for your assignment number 2. All right, so I'll continue simply to here, assuming that you're going to do that, and then you will be able to catch up, okay? Why do we want to do doubly linked list, okay? So there are basically 2 reasons for that. Let me just summarize, and then you can have some roadmap as we go through the details. So why doubly linked list. Okay? So there are two main reasons. One would be for performance. And if you recall, one of the operations that we did for singly linked list, which is remove last, that's the main one. But I would say any methods that's kind of similar to remove last, you should really watch out for. And this one here used to be linear for singly linked list. By the extension we're going to introduce in the doubly linked list is going to be constant. That's what we'll see. All right, number 2. So guys, hello. I'm not sure if you're really aware, it's really, really distracting from my side. Yeah. I'll be very grateful if you can watch out for that. Thank you. I appreciate it. All right, one thing is about performance. We're going to see the kind of extension we can introduce to the node level. All right. And the second one will be, it's more about the structure of your code. You can improve it. Code structure. All right, for the code structure over here, let me just give you a little bit sketch over here. Basically, you don't have to worry about edge cases. Edge cases. And what do I mean by edge cases? I'll show you right away. If you look at the slide, that's how we started with. For the singly linked list, I'll just give you 2 examples. If you look at how we implemented add first and also remove first, we had to add some conditional to say, for example, for add first, if the current list is simply empty, then we have to make sure after adding that very first node, we're going to update the tail and potentially the head as well. Right? So that's an edge case, meaning that you got to do some special care to edge cases, like a special condition. Usually when the resulting list is empty, or if the current list is empty. So these are the typical scenario for singly linked list. Another example would be, let's say I want to remove the first. In that case, if the current list is of size 1, that means after the removal, the list is going to become empty. In that case, I want to set the head to be null and also tail to be null, right? And etc. So these edge cases are easy to program. I'm not saying there's anything wrong with them, but it would be very nice if we don't have to worry about them. We can just focus more on programming the general cases like this. So that's what a doubly linked list can actually give to you. That's something we'll illustrate as well. You will see that we're going to define about 2 to 3 helper methods in the doubly linked list to see how we can insert in between and also remove certain nodes. And we don't have to worry about edge cases anymore. And so later on, when you actually review the notes for doubly linked list, always remember why we are doing this. 2 things. Number 1, about performance. Number 2, about the code structure. And for the code structure, it's about removing the edge cases. That's something you want to watch out for. All right? Hopefully that's at least clear for now. And we're going to exemplify exactly what I mean. So the first thing we should really do is to have some very intuitive introduction to doubly linked list. Okay, so I'll switch to the page and I'm going to do a little bit drawing and also highlight to you the differences. You can definitely go over this part of the slides. This one here, it just summarizes about what's really good and what's really bad about singly linked list. And don't get me wrong, when I say these are the situations where the singly linked list will perform poorly, doubly linked list is not going to improve all of them. It will only improve some of them. That's something you want to keep in mind. Because otherwise, what's the reason to still keep singly linked lists if everything can be improved? There are only certain methods that can be improved. I can tell you right away. If you still want to get node at a particular index, it doesn't matter if you use singly linked list or doubly linked list. They will still be linear. All right? But keep that in mind. All right, let's now do a little bit of introduction. But this part here, I'm going to do on the iPad to summarize quickly. But these slides, you can take a look. I don't need to read them off. Okay, let's see here. All right, very quick to go over the points over here. Some of them are just repetition from the case of singly linked list, but some of them are new. It will be a chain of bidirectionally connected nodes. Okay, let me just highlight bidirectionally. And think about it this way. The way, when you talk about a singly linked node, SLN, okay? The singly linked node looks like this. you have the data like an element. And also you have the next. What about doubly linked node? Okay, doubly versus singly, right? It's going to be extended by just one attribute at the node level. We still got elements, and we still got next. So up to now, thinking this way, a doubly linked node is basically still a singly linked node. Whatever you were able to do using a singly linked node, you are still able to do it using a doubly linked node because the elements and the next are still there. On the other hand, by introducing another attribute over here, there will be something that can be done by doubly linked node, but we cannot do in singly linked node. Get that relationship clear, all right? And this one here is the new attributes called previous. Think about symmetric. Previous as opposed to next. Okay, let me highlight it. So you should really remember this is the important extension. Okay? This little extension here can make sure we can improve the performance of some methods and we can improve the code structure of many methods. It's really magical. Sounds magical, but we'll see. All right, so each node here, when I say node, is really a doubly linked node. Okay? So doubly linked node over here. We got some reference to the data, like elements, next node, and previous node. Okay? And a doubly linked node or doubly linked list is still a singly linked list because you still got the next reference. Many methods will be implemented just the same way. Okay? So whatever implementation you were able to do on the singly linked list, you can still copy and paste for doubly linked list. That's not a problem. But there will be some methods that can be implemented more efficiently. Let's sketch, especially our remove last friend. Okay? Let's take a look. The most representative example would be remove last. Okay, let's take a look very quickly. If this happened to be the last node, for example, let's say this is the last node. And it's now a doubly linked node. That means you got some next over here. Also, you got some previous over here. And you got some element over here. We know that the critical step for remove last would be, we want to remove this node, of course. But more precisely, we want to remove the next reference. So there will be some next reference over here. So this will be some previous node. Let me be a little bit simplified on sketching this idea because we ought to know another two important concepts, just for now. What we need to do is to make sure this previous node will set its next to be null. That's what we want to do, right? But now we don't really need to go all the way from the beginning all the way to over here by using getNodeAdd. We don't need to. All we got to say is this node here, dot previous, is going to give me that node. That one there is going to take constant time. So this is where we can break through the performance, all right? So let me draw a little bit better, and then I think that'll be good for now, just for you to remember, okay? So this one here is the previous. Okay, so this is going to be big O of 1 for remove last. Okay, I will try to elaborate this maybe a little bit later. Okay, and if you want to access some node in a list, let's say you want to, so we still got relative positioning. So this is the part where having either a doubly linked list or singly linked list doesn't really matter. You are still restricted by relative positioning. Let's say you got a list of doubly linked nodes. Let's say over here, next, previous, and previous. Let's say if I want to go to some position I, it doesn't really matter if I got a previous reference or not, because I can either go this way from the end or I can go this way from the beginning. It will be just linear time. Doesn't matter, because in general, it can be just in the middle. All right? So relative positioning will be big O of n. So here, having the previous reference does not help. And this is the part where I said not necessarily all the performance for all the method for singly linked list can be improved, can be achieved by doubly linked list. And this part will be the same. The chain may grow and shrink dynamically like a singly linked list. And this is the part we have to learn. Header and also trailer. Okay, I'm going to draw right away. But that will be the new terminology you will have to get used to. For singly linked list, we talk about head and tail. For doubly linked list, we talk about header and trailer. Okay, let's now visualize them. They are not difficult, but I just need to clarify. Again, let's compare side by side. We got singly linked list. And also we got doubly linked list. All right, we got these two. What's going to happen is, I will also show you the Java class declaration in a moment. For singly linked list, let's recall. We have some class called singly linked list, where we got the head, we got the tail, and also we got the size, right? These are all nice stuff over here. Let's start with the empty list. For empty list, it's going to be head pointing to null, the tail pointing to null, and the size will be just 0. That's a singly linked list being empty. What about doubly linked list? Let's take a look. A doubly linked list is going to be some class called doubly linked list. Doubly linked list. So we got something called header, we got something called trailer, and we may have size as well. No head and no tail. Okay, like that. Now, what's really the difference? In the case of empty doubly linked list, the header and trailer will not be null. They are dedicated nodes, as you will see on the slide. They always exist. Let me draw that. The header is going to point to, let me try. Okay, the header is going to point to some doubly linked node over here. Also, the trailer is going to point to some doubly linked node as well. Okay, oh, sorry. Okay, and let's be careful here for draw. Okay, let's now see what's going to be the reasonable storage in these two dedicated nodes. Oh, by the way, the header and trailer, they have some different names for that. Sentinel. Sorry. I kind of forgot about the spelling. It's called sentinels or guards. Okay. They don't really store anything meaningful. So for the element part, they simply point to null and point to null. That's the element part. In the case of the header, it's the very first node conceptually. So its previous will be just null. Symmetrically, the next for the trailer will also be null. Right? In the case of the empty list, this is what we have. The next of the header is going to be the trailer. The previous of the trailer will be the header. So this is the previous reference. This is the next reference. And this one is the previous reference. And this one here is the next. Sorry, I'll write a little bit better. The next reference. Okay, are we okay with the empty structure? Okay. It is so important for you to know about the structure, what's going to happen at the runtime. And of course, if we try to create more and more nodes into the list, in the case of singly linked list, let me just draw very quickly here. The head is now going to point to some node. And eventually, also the tail is also going to point to some node. That's something we're very familiar with. And what we're going to see will be, how do we insert more nodes in between? Let's say for the very first node, if I want to put a node over here, let's say it's a doubly linked node, what's going to happen is the next of the header is now going to point to this first node. And the previous of the trailer is now going to point to this node over here, right? And then, of course, the data, the element part is going to point to some meaningful objects. That's what's going to happen. Okay? Now, for now, I just want you to understand more about empty structure. when some nodes should really go in between, we're going to draw lots of diagrams to show that. Are we okay so far about the header versus trailer? Thank you. Okay, let's now try to see if there's anything missing. Right, what about in Java? So this node class is already generic, but I can just go over with you quickly about how to see the node class. Let's take a look. So 2 classes we have to worry about. Okay, let's take a look. So the node class over here, you can think about this node here is doubly-linked node. It's a doubly-linked node. Oh, you might be wondering, for your programming test number 1, are you going to be given a doubly-linked node or singly-linked node? Here's the answer, singly-linked node, not doubly-linked node. That means you don't have the previous reference, so you don't want to change that class. Okay? I'll make sure I put it clear on the PDF guide. And for the node class over here, you can see we got element, we got next, we got set element, set next, get element, get next. So these are all the same from the singly linked node before. The only thing that's new is over here. So we got the previous reference, we got get previous, and also we got set previous. All right? And we got some constructor over here, which I'll trace together with you, just to make sure. All right? And again, you want to make sure you understand what this really means. Okay? That's in your assignment number 2, background video. Please check them out. All right? And what about at this doubly-linked list level, right? So here I just give you some attribute size, maybe initially 0. There should be another header and trailer, which I didn't list over here, but it's header, oh, sorry, over here, header and trailer. Didn't see that. So you can see header and also trailer. And one thing to note, you can see the node over here is really referring to the node over here. Okay? And what we should do now is just to show to you how to create an empty doubly-linked list very quickly. Let's trace that. Okay? Again, this will be some source code I will make sure I made available to you. You can play with them, use a debugger, use a breakpoint, and make sure you really understand the code. Okay? So what we do is we're going to execute, let's say, this line. We're going to create a list of type doubly-linked list. And it is a feature of a generic list. You can simply say, I'm going to store elements of type string throughout the list. Okay? And then this list over here is actually going to point to a doubly-linked list objects. Okay? Let me put it here. So it's going to be a doubly-linked list objects. Okay, over here. But how exactly is the constructor over here going to be executed? It's over here. Okay, I will highlight them. So this constructor over here, you should really look at here. Doubly-linked list constructor. Let's make it a little bit bigger. Okay, I'll let you read the 3 lines of code very quickly, and then I will trace that together. 1 here, 2 here, and 3 here. Okay, take a look just for 1 moment. It's somehow similar to how you can initialize, well, I would say more sophisticated than initializing a singly linked list. In the case of singly linked list, you just set a head and tail to be null. That's it. But now for here, we have to create a trailer and a header, like what I drew to you earlier. All right, so overall, we're going to create some header, create some trailer. Each one of them will be something like this. Here, you can see we are passing something null or not null. This is where you want to watch out for. And then we're also going to set some reference over here. Let's now take a look to see how these 3 lines can be executed. All right, let's take a look. Let's start with the first line. Let's say the first line over here, we're going to create a header. Okay, so we have the header attributes. This will be the header attributes, right? Okay, I'll just draw as I go. So header is actually going to point to a new node. That node itself, you're going to look at this constructor over here. And the convention that we're going to adopt, you're going to pass 3 input arguments. The reference to the elements, the data, the reference to the previous, and the reference to the next. You're going to set them accordingly. Okay, let me say it again. When you create a new node, doubly linked node, you need to pass 3 references. Reference for the data, reference for the previous, and reference for the next. So if you compare with the constructor for singly linked node, this is the new addition. Right? Let's take a look. So for the header part, everything will just be null. That's easy to visualize, right? So header is actually going to point to a new node over here. That's doubly linked node. Okay. That one there is going to be null, null, null. Okay. So the previous will be just null. The next will be null. And also the elements will be null as well. All right, so that's the first line, header. What about trailer? If I try the trailer, let me use purple. How about that? Trailer. Oh, sorry. For the trailer, we're going to, again, calling the constructor for the node. And this time, elements will be null. The sentinels or the guard nodes, header and trailer, they never store any meaningful data. So data should always be null. Okay? So I'm going to highlight it. So now here and now here. And the previous node is going to be header. The next node is going to be null. Right? Notice that. And I want to point out to you that something we didn't really assess you on, but there's something you ought to know. We are passing the header over here as P. That's something called call by value. All right? Call by value. Just remember. Okay? So what this will do, let's now visualize it. So we got the trailer node over here. Right? Trailer. And then it's also going to point to a new node, which I'm going to draw right here. Okay. Let me just get rid of this. And that one there is going to be another node over here. And let's see how we can do it. The data is going to be null. Always null. And the previous is going to be wherever the header is. The previous of the trailer is going to be wherever the header is. So that's aliasing. Okay? Over here. And then, so that's the previous. And after this, of course, the next will be also null. And now you can see the only thing that's left is about setting the next reference of this to be this. And that's really what this line is doing. Header does set next to be trailer, right? This one is going to make sure that one dot next is the trailer. All right. Guys, are we okay about this? That's the most fundamental code you need to know how to visualize and trace, about how to build a doubly linked list. Okay. Some aliasing test to show to you. If you try, just for example, if I say list dot header, which is list dot header, is pointing to this particular objects. You can see there is another path that's pointing to this object, which is from here, from the trailer, right? Agree? So how do I write it down? I can say list dot header will be equals list dot trailer dot previous. Right? You can see they are pointing to the same objects. Header, the same as trailer dot previous. So they are the same objects. Equal should be true, right? And I'll leave that as an exercise for you. What would be another path for list dot trailer? Equals what? Okay, that'll be some exercise for you.
Because obviously we're making a list of some sort of variables.
Mm-hmm.
Right? I know we're initializing header and trailer to have no spaces.
Yeah.
But when we actually are executing it, do we actually add something to header and trailer, or do we expand between them?
Sorry, can you just say it again? I don't quite catch exactly.
When we're initializing our list.
Yes.
And we're adding our first variables and so forth. Our header, We consistently keep that.
I see what you mean. Yes, good question. The question is, will there be any time, let's say after the initialization here, we got the header node and the trailer node. Would there be any scenario where we have to get rid of maybe this node, for example? No. The header and trailer, once you initialize the empty list, always stay there. They will never be even temporarily removed. They will always be there. You will see that the beauty about having the header and trailer is just by defining some helper method, we will be able to actually define other operation in the doubly linked list in a much more elegant way. You will see how. But these two nodes are always there. You never delete them. They're always there. Say it again, sorry. Yes, exactly. So, good question here. We'll see that very soon. Let's say I want to add a new node here that should really go between these two nodes, header and trailer. And the nodes previous should be the header, and the nodes next should be the trailer. Yes, that's what we'll do. Yes? They don't store any data. So that's why they're called sentinels or guards. Their main purpose is to guard other nodes. You can think that way. So that's why the reference over here should always be null for the elements. You should not store any meaningful data. That would just make somehow your algorithm confusing. Yeah. That's the important point. Yes. Absolutely. Good. All right, guys, we got about maybe 13 minutes or so. I would suggest we try to go over some coding example for doubly linked list. You get the idea. I don't think I can finish everything today, but I think we can continue after the reading week. Let's see how much we can do. I'll still finish in time for today. Okay, so that's about the two classes that we spoke about, right? We just did the tracing together with you. And header trailer. All right, so this is really important. This is something I just mentioned before, right? If I want to improve the performance for remove last, I can definitely do that. Think about what's going to happen. So this one here is about trailer that get previous, that get previous. Okay, I need to draw a little bit. Okay, so here, let me draw. Okay, I'll show you exactly what that line really means. Let's say we got the header and the trailer. Okay, let me ignore this doubly linked list objects. So this is the header. Okay, let me just copy this. So, okay, header should be here. Let's say I got three nodes in between. Okay, yeah, I'll try to improve the diagram. Let's say header is pointing to here. And the trailer is pointing to over here. Let me set the references quickly. The elements will just be null. The elements will just be null. All right, and then let's say for the meaningful nodes, that's inside. Let me just use blue. All right, oh, forgot about this one here. Okay, conceptually, think about this will be the very first node. Index 0, index 1, and index 2. Header and trailer are not considered as part of the chain. They're there to help us make things a little bit easier. But when you say, I want to get node at index 0, this is the node you want to get. All right, just remember that first. And let's set the references very quickly. For the next reference, header.next is pointing to the next first node, next, and also next, and also the next. The next of last node is the trailer. Right, that's obvious. And let's also get the previous. Previous over here, previous over here, previous over here, and previous over here. Right, that's really the structure that we're going to build. And what does this line here really mean? If I want to remove last, I know that I need to get the second last node. How do I do that in the case of doubly linked list? This is the last node. Second last node is this, right? Let's now make a note here. Second last node. How do I get there? I got reference to trailer. trailer dot previous gets me the last node, and then dot previous gets me the second last node. That's exactly what the slide is trying to say. So this will be trailer dot previous dot previous. And of course, big O of 1, right? Only about attribute access, about the previous reference, second last node specifically. In a more general sense, if I am given the reference to some node in the middle, let's say for some reason I need the previous node. In the case of singly linked list, as we talked about in the beginning of today, we had to use get node at from the beginning to get to this point, right? But now for doubly linked list, what should we do? Just get previous, constant time. Right? You can see visualizing the structure here should really help. All right. Okay, and let's see, it will help us simplify the logic. And also, yeah, so this part here just about, you will see we can call helper method to really implement many others. That's basically the point. Let me try to see if I can do at least one helper method for today. Give me a moment. Okay, good. Let's say we want to define some common helper method for insertion. And the diagram here, you can look at that. I'm going to draw something similar anyway. This will be the method we want to implement. It's a helper method. It's a very general one that we can reuse for many others. This method here is called add between. Okay, let's now take a look of this method here. So given some data for which we want to create a new node, we want to add this new node between some predecessor and some successor. All right, so what do we want to do? Think about the predecessor here. Predecessor here is this reference. And presumably the successor over here should be the node that's simply next to the predecessor. They are neighbor of each other. That's the implicit assumption we are making. The way we're going to call the add between, you will see exactly the point. Okay? So we have some assumption. The predecessor, the next, should be the same object as the successor. Symmetrically, successor, the previous, should be the same as the predecessor. And the way we ensure this is the way we're going to call the add between will ensure that. Just keep that in mind. We'll see. Okay? Right? Having this in mind, we got predecessor, we got successor. What we want to do is we want to create a node in between over here. That's why it's called add between. All right? Let's now execute line by line to see what's going to happen. Line number 1, we are going to create a new node, which is going to store E. The previous should be predecessor. The next should be successor. Okay, let's try. So I'm going to create a new node over here. And this new node over here, let me just say node. That one there is going to have next, previous, and also data. Right? By the way you visualize a node can be either this way here, or if you prefer, you can visualize in this way. See which way might be better for your purpose. Sometimes it might be better to do it here, and sometimes it might be easier to do this. I'll do both. All right, so we got first of all, the elements, which is just going to point to this element here. Also, we got the predecessor. Oh, sorry, we got the previous and next. We got the previous, and also we got the next. All right. You can see here the previous should be the predecessor. So the previous should be the predecessor. And the next should be the successor. Are we okay with this? That's the first step. Apparently, you can see this one here is not good enough because this list structure here doesn't make sense. Somehow you can see the next of this node here is still pointing to this one here. It should be pointing to this one instead. We've got to build that consistency. Right? Let's see how we can fix it. The next one, predecessor dot set next to be the new node. Predecessor dot set next to be the new node. Rather than pointing to over here, it's actually going to point to just the new node. That's what this line will do. Next one, successor dot set previous to be the new node. successor over here dot previous over here, rather than pointing to here, it's now going to point to this node over here. And of course, you got to update the size attribute as well. What's the resulting structure? Let's now highlight. Resulting structure goes like this. We got the predecessor over here. Its next is pointing to this node. That node's next is pointing to this node. You can see we got this, and then this, and then this. Symmetrically, we also got the previous node set properly. For the successor, its previous node is over here. For the new node, its previous is pointing to over here. So you can see we go from here, go to the previous, and go to the previous. So the structure is still consistent. Okay. This helper method is very powerful. I'll just give you some example about how we can call this helper method, ferrets. Mm-hmm. Good question. Very good. So Farrah's question goes like this. Hypothetically, let's say we only do this line, and we forget about these two lines, let's say. That's what you're asking, right? Okay. In this way, you're basically not doing anything useful. I'll tell you why. Okay, let me just write this. Yeah, so these two lines, without these two lines, the new node remains unreachable. I'll show you why. Unreachable from the chain that we added into. The unreachable here is really the keyword. Let's see how. Let's say this is still pointing to here. This one is still pointing to here. Let's say we start with this chain. What will be the next one? It will be still this one. It's not reaching here. And also for this node here, if we go back here, it's still reaching here. We still don't have this node. So it's like this node itself is trying to get reached to these two nodes. But from the original chain, it cannot really reach over here. So that's a logical error. You wouldn't get any exception or any runtime error, but this will be some logical error you definitely want to avoid. Otherwise, later, when you actually want to traverse, let's say, the list over here, you still cannot reach over here. That's really a critical insight. No, Java definitely wouldn't tell you. So let's say you get rid of these two lines, you might be able to pass on test cases, but it's going to impact about the structure for your chain, which might make other methods executed wrongly. At some point, you might just get into null pointer exception. I don't know, at some point. Yeah. Mm-hmm. Very good. So these two lines afterward are very, very needed. Question?
If the size of the chain is one or less, can still use this method?
Say it again, sorry.
If the size of the chain is one or less.
Okay, so yeah. So add between doesn't assume about the size of the list. It can be, let's say the current list is empty. You will see that. If the current list is simply empty, you can definitely use this one to add between the head and the trailer, exactly. Right? Let's say if the current list as it has, let's say several nodes in the list. For example, let's say this. Let's say I want to add first into this. Right? I have this node. How do I add it as a first? I can add it between the header and header.next. Right? How can I add last? Add between the trailer and trailer.previous. Guys, it makes sense visually, right? Okay, good. Very good. All right, I'm running out of time. If you don't mind, I'll take just 1 minute to recap very quickly. And then I'll see you after reading week. Just give me 1 minute, please. So I think our plan definitely is to really spend the Wednesday lecture, because for the Monday lecture time, you're going to have your programming test 1. But for the Wednesday lecture, after the reading week, I'll definitely finish off the Doubly-Linked List so we can start covering the further topics. But we definitely finishing something very fundamental. What will be your best interest during the reading week? Please make sure you complete the background study for your assignment number 2. Try to struggle through the assignment, submit in time to get the credits, And then I'm going to give you some practice problem as well for programming test 1. Most importantly, review what we have covered about this fundamental data structure. It's going to impact about the understanding for later. Thank you so much. I will see you after the reading week.